breaking news about Bitcoin.
Supposedly most stable cryptocurrencies took a massive tumble.
Bitcoin, the digital currency created a dozen years ago, is exploding in value.
Blockchain technology, with its decentralized nature, is built on the premise of trust and security. Unlike traditional systems that rely on centralized authorities to manage data and ensure its security, blockchain employs cryptographic techniques and distributed networks to protect its data. Security is the backbone that ensures blockchain systems are resilient, trustworthy, and reliable. Blockchain networks, by design, are decentralized, which eliminates single points of failure. However, this decentralization also introduces new security challenges. Without a central authority to oversee operations, blockchain must rely on mechanisms that ensure all participants act in the network's best interest. This is where cryptographic methods, consensus algorithms, and trust mechanisms come into play. Data integrity and tamper resistance. One of the most crucial security features of blockchain is its ability to maintain data integrity. Once data is added to the blockchain, altering it becomes nearly impossible due to its cryptographic structure. Each block contains a reference to the previous block in the form of a cryptographic hash. This creates an interconnected chain of blocks where any attempt to modify one block would require altering all subsequent blocks. Given the computational power required to do so, it becomes practically infeasible for an attacker to succeed, ensuring that the data remains tamper-resistant. This inherent feature of blockchain immutability provides a high level of data integrity. It guarantees that once data is written to the blockchain, it cannot be changed or tampered with, creating a transparent and verifiable record of all transactions. This security feature is particularly valuable in industries like finance, healthcare, and supply chain management, where data integrity is paramount. Consensus mechanisms. In traditional systems, a central authority is responsible for verifying and validating transactions. In contrast, blockchain relies on consensus mechanisms to achieve agreement among participants on the state of the ledger. These mechanisms are crucial to ensuring that only valid transactions are recorded on the blockchain, maintaining its integrity. There are several types of consensus mechanisms, each with its strengths and weaknesses. Proof of work, POW. This mechanism requires participants, known as miners, to solve complex mathematical problems to validate transactions and add them to the blockchain. The computational effort needed to solve these problems acts as a deterrent to malicious actors, as the cost of attacking the network becomes prohibitively high. Proof of stake, POS. POS selects validators based on the number of tokens they hold and are willing to stake as collateral. This system incentivizes validators to act honestly, as they risk losing their staked tokens if they engage in malicious behavior. Delegated proof of stake, DPoS. DPoS allows network participants to elect a small group of trusted delegates who are responsible for validating transactions. This system improves scalability while maintaining security through regular voting and accountability. These consensus mechanisms are essential for ensuring the security of decentralized networks. By encouraging honest behavior and penalizing malicious actions, they help maintain the integrity of the blockchain. Common security, threats and vulnerabilities, understanding the risks. Despite its robust security features, blockchain is not immune to threats. Understanding the most common risks is essential for developing effective security strategies. One of the most significant threats to blockchain networks is a 51% attack. This occurs when an attacker gains control of more than 50% of the network's computational power, or stake. With majority control, the attacker can manipulate the blockchain by double spending coins, censoring transactions, or preventing new transactions from being confirmed. While larger, more decentralized networks are less vulnerable to such attacks, smaller networks with fewer participants are at greater risk. Sybil attacks, flooding the network with fake identities. In a Sybil attack, an attacker creates multiple fake identities or nodes to gain disproportionate influence over the network. This can disrupt consensus, manipulate voting mechanisms, or flood the network with false information. Implementing reputation systems or requiring identity verification can help mitigate the risks associated with Sybil attacks. Smart contract vulnerabilities. Smart contracts, while revolutionary, are not without their vulnerabilities. These self-executing contracts rely on code, and any errors or bugs in the code can lead to unintended behavior or financial losses. Issues like reentrancy attacks or logic flaws can be exploited by attackers. To prevent these vulnerabilities, rigorous testing, code audits, and formal verification are necessary before deploying smart contracts. Phishing and social engineering. While blockchain's cryptographic security is strong, attackers often target the human element through phishing and social engineering attacks. By tricking users into revealing private keys or passwords, attackers can gain unauthorized access to user accounts. Educating users on security best practices and implementing strong authentication methods are crucial for preventing these types of attacks. Trust mechanisms in decentralized systems. Blockchain technology eliminates the need for a central authority, but trust remains a critical component. Several mechanisms are in place to build and maintain trust among participants. Cryptographic techniques, public key cryptography, and cryptographic hashing play a crucial role in establishing trust in blockchain networks. These techniques ensure that data is secure, transactions are verified, and once added, the data cannot be altered. The transparency and immutability offered by cryptography build confidence among participants. Reputation systems. Reputation systems evaluate and rank participants based on their behavior and contributions to the network. Participants with high reputation scores are more trusted, while those with lower scores face restrictions. This incentivizes participants to act in ways that enhance network security and build trust within the community. Decentralized identity management. Blockchain allows users to manage their identities in a decentralized manner. With decentralized identity management systems, users can control their personal information securely without relying on a central authority. This enhances privacy and trust while providing a tamper-resistant method for identity verification. Transparent governance. Transparent governance mechanisms, such as on-chain voting, allow participants to have a say in the network's decisions. This transparency fosters trust, as participants know that they can influence the direction of the network and hold decision-makers accountable. In conclusion, blockchain technology offers significant advancements in identity management and governance. By enabling decentralized control of personal data and fostering transparent decision-making processes, blockchain paves the way for a more secure, inclusive, and trustworthy digital environment.